You think you know your heart. You've seen it drawn on greeting cards. A simple red shape, symmetrical, clean, two gentle curves meeting at a point. You've felt it after climbing stairs too fast, that insistent knocking against the inside of your chest, demanding to be noticed. You've probably pressed two fingers to your wrist at some point and counted the beats, watching the second hand on a clock, feeling vaguely reassured that the number was somewhere in the normal range. You've heard it described 1,000 times, in health class, in doctors' offices, in fitness apps that track your resting rate while you sleep. You think you understand what it is. A pump, a muscle, a reliable if somewhat unexciting piece of biological machinery that keeps the blood moving while your brain does all the interesting work. But here is what nobody tells you. Here is the fact that most people go their entire lives without truly absorbing, even though it is happening inside them every single moment of every single day. Right now, as you are watching this, as your eyes move across these words, as some part of your mind is already deciding whether this video is worth your time, your heart has beaten more than 100,000 times today. Not approximately, not roughly. The average adult heart beats between 60 and 100 times per minute, which means that since you woke up this morning, your heart has already completed somewhere between 86,000 and 144,000 individual contractions. Each one a complete mechanical event, each one involving the coordinated movement of billions of cells, each one generating enough pressure to push blood through a vascular network that if you unrolled it end to end would stretch for approximately 60,000 miles. 60,000 miles. Let that sit for a moment. The circumference of the Earth at the equator is roughly 24,900 miles. Your circulatory system, laid out in a straight line, would wrap around the planet more than twice. And your heart is driving fluid through all of it. Right now, without being asked, without being reminded, without stopping for even a fraction of a second to recover. By the time you finish watching this video, let's say it runs about 20 minutes, your heart will have added somewhere between 1,200 and 2,000 additional beats to today's total. And then it will keep going through dinner, through whatever you watch before bed, through the hours you spend asleep when your conscious mind goes dark and your heart slows slightly but never ever stops. Tomorrow it will do it again. And the day after that. And the day after that. The average human heart beats approximately 100,000 times per day. That is 35 million times per year. Over the course of an average human lifespan of roughly 78 years, and accounting for the fact that the heart begins beating around 3 weeks after conception, before the person it belongs to has eyes or fingers or a name, the total number of lifetime heartbeats comes to somewhere between 2.5 and 3 billion. 2.5 to 3 billion continuous mechanical cycles, without a single scheduled maintenance window, without replacement parts, without the ability to shut down, run diagnostics, and restart. Now think about what that means in engineering terms. The most durable mechanical pumps ever built by human hands, industrial circulation pumps used in nuclear power plants and deep-sea oil extraction equipment, rated for continuous operation under extreme conditions, are designed to last for approximately 50,000 to 100,000 hours before requiring major service. That is roughly 6 to 11 years of uninterrupted operation. Engineers consider this an extraordinary achievement. These machines are made from hardened steel alloys, ceramic bearings, and synthetic seals engineered at the molecular level to resist wear. They are monitored continuously by sensors, maintained by specialist technicians, and replaced the moment their performance begins to degrade. Your heart does not have sensors. It does not have a maintenance team. It is made of soft biological tissue, protein filaments, cell membranes, water, materials that, by every intuition we have about durability and wear, should fail catastrophically long before they reach 3 billion cycles. And yet here you are. This is the engineering mystery at the center of this video. Not why the heart beats. That question, at least at the surface level, has a reasonably well-understood answer. But why it never gets tired. Why it doesn't wear out the way every other muscle in your body wears out. Why it doesn't fatigue the way materials fatigue. Why a structure made of some of the most delicate biological material in the human body outperforms, by orders of magnitude, the most sophisticated mechanical pumps that human civilization has ever produced. I know what you're thinking right now. You're thinking, it's just a muscle, and muscles work all the time. What about the diaphragm? What about the muscles that keep your eyes moving, or the ones that maintain your posture? Aren't they working continuously too? Fair point. And here's why it doesn't resolve the mystery. The diaphragm does work continuously, but it rests between breaths, real, measurable rest periods where muscle tension drops almost entirely. Postural muscles work in rotating shifts, with different fiber types trading off load so that no single set of fibers is under continuous tension. Even the muscles that move your eyes cycle through micro-rests that are invisible to conscious experience, but very real at the cellular level. The heart does not do this. The heart contracts, fully, forcefully, with the complete coordinated engagement of its muscle mass, and then relaxes, and then contracts again, and it does this without rotating shifts, without fiber-type trade-offs that allow individual cells to rest while others work, without any of the fatigue management strategies that every other muscle in your body relies on to keep functioning over time. And yet it doesn't fatigue. That is not a small thing. That is not a trivial biological detail. That is one of the most extraordinary facts in all of physiology, and most people walk around carrying it in their chest without ever stopping to wonder why. There's another layer to this mystery that makes it even more remarkable. Your heart is not running at a gentle, conservative pace designed to minimize wear. It is running hard. Every single beat of your left ventricle, the main pumping chamber that drives oxygenated blood into your arterial system, generates a peak pressure of around 120 millimeters of mercury. That is the number at the top of a healthy blood pressure reading. What that number represents, physically, is the force required to push a column of liquid mercury 120 millimeters into the air. Applied to the geometry of your circulatory system, it is enough pressure to drive blood from your heart to your fingertips and back in less than 60 seconds under resting conditions, and significantly faster during exercise. During intense physical exertion, a sprint, a heavy lift, a moment of genuine fear, cardiac output can increase fivefold. The heart doesn't just speed up. It beats harder, pumping more blood per contraction, driving pressure higher, delivering more oxygen to muscles that are suddenly demanding it at a rate that would have seemed impossible at rest. The transition from resting to maximum output can happen in under 30 seconds. No mechanical pump on Earth scales its output fivefold in 30 seconds without significant stress to its components. Your heart does it every time you run for a bus. And then, when you catch the bus and sit down and your breathing slows, your heart scales back down, smoothly, proportionally, without any active intervention on your part. You didn't tell it to speed up. You didn't tell it to slow down. It read the signals from your body, chemical signals, neural signals, pressure signals from the walls of blood vessels, and adjusted its behavior accordingly, autonomously, in real time. Think about the last time someone startled you. Not a mild surprise, a genuine shock, the kind where your stomach drops. In the fraction of a second after that startle, before your conscious mind has even fully processed what happened, your heart rate has already spiked. The signal traveled through your nervous system faster than thought. Your heart responded before you knew there was anything to respond to. This is what we mean when we say the heart never gets tired. It's not just that it keeps beating, it's that it keeps beating with full responsiveness, full adaptability, full precision, across a lifetime of demands that range from the stillness of sleep to the extremity of maximum exertion in response to signals that arrive from every system in the body simultaneously, without ever reaching a state where it says, "I need to stop." So why? What is the mechanism? What does the heart have that a steel pump doesn't? What does the cardiomyocyte, the cardiac muscle cell, know about continuous operation that the engineers who build industrial machinery are still trying to figure out? The answer, as it turns out, is layered. It operates at the level of cellular architecture, at the level of electrical physics, at the level of metabolic chemistry, and at the level of mechanical design. And to understand any of it, we need to start where all good science starts, not with the answer, but with how badly and for how long the smartest people in the room got the question wrong. Because for more than 1,000 years, the most educated minds in the Western world looked at the heart. They studied it, they theorized about it, they built entire cosmologies of medicine around it, and they missed almost everything important about how it actually works. That story begins in ancient Greece, moves through the dissection rooms of Renaissance Europe, and arrives at a moment in 1628 when a quiet English physician named William Harvey sat down with a set of measurements that didn't add up and changed everything. But before we get there, I want you to do something. Put your hand on your chest, not for long, just for a moment. Feel that rhythm, count 3 beats. What you're feeling is not simple. What you're feeling is the output of a system so precisely engineered, so deeply integrated with every other system in your body, so quietly extraordinary in its operation, that the more closely you examine it, the harder it becomes to believe it evolved by accident. Whether you think it did or didn't, that's between you and your philosophy. But the engineering is real, and it is waiting for you in everything that follows. For nearly 1500 years, the smartest people on Earth believed the heart was on fire. Not as a poetic metaphor, not as a spiritual symbol, though it was certainly that too. As a literal physiological fact, as the foundational assumption upon which an entire system of medicine was built, taught, practiced, and defended, with the full weight of institutional authority, religious sanction, and academic prestige, across more than 60 generations of physicians, scholars, and healers. The heart, they said, was a furnace, and the blood was its fuel. To understand how a civilization as sophisticated as ancient Greece arrived at this conclusion, you have to understand the tools they were working with. There were no microscopes. There were no blood pressure monitors. There was no germ theory, no cell theory, no understanding of electricity or chemical signaling. What ancient physicians had was observation, careful, systematic, genuinely impressive observation, combined with a set of philosophical assumptions about the nature of the body that seemed entirely reasonable given what they could see. And what they could see was this. The heart was warm, warmer than the surrounding tissue, warmer than the skin. When you placed a hand on a living chest, you felt heat. When a person died, the body cooled. When a person was sick with fever, the pulse quickened and the skin burned. The connection between heat and life, between warmth and vitality, seemed self-evident. The heart, sitting at the center of the body, generating more heat than any other organ, must be the source of that vital fire. This intuition was formalized by the Greek philosopher Aristotle in the 4th century BC. Aristotle was not primarily a physician. He was a natural philosopher, a systematizer, a man who wanted to explain everything in terms of underlying principles. And the principle he identified at the center of animal life was what he called the innate heat, a biological fire that animated living bodies, distinguished them from dead matter, and resided in its purest and most powerful form in the heart. For Aristotle, the heart was not just a pump or even primarily a pump. It was the seat of sensation, of emotion, of intelligence itself. The brain, in his view, was a cooling organ, a radiator whose function was to prevent the innate heat of the heart from burning the body alive. This is why, Aristotle argued, intelligent animals had larger brains. They needed more cooling capacity to manage the greater heat of their more vigorous hearts. It sounds almost charming now. But remember, this was not fringe thinking. This was the dominant intellectual framework of one of the most sophisticated civilizations in human history, articulated by a man whose works on logic, biology, physics, and ethics remained authoritative texts for nearly 2,000 years. When Aristotle said the heart was the seat of intelligence and the brain was a cooling mechanism, professors were teaching exactly that in European universities well into the 16th century. Then came Galen. Claudius Galenus of Pergamon, Galen as he is known to history, was a Greek physician who worked in Rome in the 2nd century AD, serving as personal physician to the Emperor Marcus Aurelius. Galen was, by any measure, a towering intellect. He was a prolific writer. His surviving works fill 22 volumes in modern translation, and an obsessive anatomist who performed thousands of dissections on animals, particularly pigs and Barbary macaques, whose internal anatomy he extrapolated, not always accurately, to humans. In an era when human dissection was socially and legally prohibited throughout most of the Roman world, animal dissection was the best available tool, and Galen used it with extraordinary rigor. His model of the cardiovascular system was, for its time, genuinely sophisticated. He understood that the heart had chambers. He understood that blood moved through the body. He understood that the arteries and veins were distinct systems carrying different types of blood. Venous blood, dark and thick, manufactured by the liver and carrying nutrition to the tissues. Arterial blood, bright red and thin, infused with pneuma. Vital spirit, in the lungs and carrying life force to the organs. What Galen got catastrophically wrong was the mechanism. In his model, blood did not circulate, it was consumed. The liver continuously manufactured new blood from digested food, which then flowed outward through the veins to nourish the body, was used up and was replaced by the next meal. Meanwhile, a small amount of venous blood seeped through tiny invisible pores in the septum, the thick wall dividing the left and right chambers of the heart, into the arterial side, where it mixed with air drawn in from the lungs and became the vivified arterial blood that carried vital spirit to the brain and muscles. The heart itself, in Galen's model, did not so much pump as breathe, expanding to draw blood in, contracting to push it out, functioning more like a bellows than a piston, its primary role being to fan the innate heat and maintain the vital spirit rather than to mechanically circulate a fixed volume of fluid. This model had enormous explanatory power within its own framework. It accounted for the visible differences between venous and arterial blood. It explained why cutting an artery was more immediately lethal than cutting a vein. It provided a coherent account of how food became energy, how lungs interacted with the heart, why fever accelerated the pulse. For a pre-microscopic age, it was not unreasonable. And it was wrong, almost entirely wrong, in ways that would not be corrected for 1400 years. The reasons for this remarkable persistence of error are worth understanding, because they tell us something important about how scientific knowledge actually advances, which is rarely in clean, triumphant leaps, and almost always through a messy, contested, socially complicated struggle against the weight of existing authority. Galen's works were preserved through the Islamic Golden Age, translated into Arabic by scholars like Hunayn ibn Ishaq in the 9th century, who transmitted them back to Europe through the great translation projects of the 12th century. By the time European universities began teaching medicine systematically in the 13th century, Galen was not just a source, he was the source. His texts were canonical. To contradict Galen was not merely to offer a different scientific hypothesis. It was to challenge an authority whose prestige was intertwined with the authority of ancient wisdom itself, which in medieval Europe was intertwined with religious authority, which was intertwined with social and institutional power. Physicians who contradicted Galen risked their reputations, their positions, and occasionally their safety. And yet the contradictions kept accumulating. The Belgian anatomist Andreas Vesalius, working at the University of Padua in the 1540s, performed systematic human dissections, by then legally permitted under carefully controlled conditions in Italian universities, and published his findings in a monumental illustrated atlas called De Humani Corporis Fabrica in 1543. It was one of the most important books in the history of science, and in it, Vesalius noted, carefully and diplomatically, that he had searched extensively for Galen's hypothetical pores in the cardiac septum, the tiny holes through which venous blood was supposed to seep from the right side of the heart to the left, and could not find them. He did not conclude that Galen was wrong. He concluded essentially that the pores must be too small to see, because the alternative, that Galen's entire model was incorrect, was still too structurally destabilizing to state directly. Even Vesalius, one of the greatest anatomists who ever lived, could not quite bring himself to take the final step. That step was taken by William Harvey. Harvey was born in Folkestone, England, in 1578. He studied at Cambridge and then at Padua, the same university where Vesalius had worked, still the leading centre of anatomical research in Europe. He returned to England, built a successful medical practice in London, and eventually became physician to King James I and later King Charles I. He was, by all accounts, a careful and methodical man, not given to dramatic gestures or revolutionary proclamations. What he was given to was measurement. At some point in the early decades of the 17th century, Harvey began doing something that seems almost embarrassingly simple in retrospect. He measured the volume of the left ventricle at rest, approximately 2 fluid ounces, roughly 60 milliliters. He estimated that the heart contracts at least 1,000 times per half hour, a conservative estimate. He multiplied 1,000 contractions times 2 ounces equals 2,000 ounces of blood pushed into the arterial system every 30 minutes. That is approximately 54 kilograms, about 120 pounds, of blood per half hour. The average human body contains roughly 5 liters of blood. Total. If Galen was right, if blood was continuously manufactured by the liver and consumed by the tissues, then the liver would need to produce 120 pounds of new blood every 30 minutes. The body would need to consume an equivalent mass of food to manufacture it. The math was not just implausible, it was physically impossible. The only explanation that fit the numbers was the one Harvey published in 1628 in his 72-page treatise. The blood circulates. The same blood goes out through the arteries, returns through the veins, passes through the heart, and goes out again. It is not consumed. It is recycled. The heart is not a furnace or a bellows. It is a pump driving a closed loop. Harvey was right. The evidence was overwhelming. The logic was airtight. His colleagues thought he was insane. His practice fell apart. Patients avoided him. Fellow physicians wrote devastating critiques. The French physician Jean Rioland, one of the most respected anatomists in Europe at the time, published a full refutation, arguing that Harvey's observations might be real, but his conclusions were impossible because they contradicted Galen. Harvey responded with characteristic patience and precision, restating his evidence, refining his arguments, and waiting for time to do what logic alone could not. He was vindicated within his own lifetime. By the time Harvey died in 1657, circulation was the accepted model in most of European medicine. The discovery of capillaries by Marcello Malpighi in 1661, the tiny vessels connecting arteries to veins that Harvey had predicted but never seen, closed the final gap in the circulatory picture. But Harvey's triumph left an enormous question unanswered. He had proven what the heart does. He had not explained how it keeps doing it. Why doesn't this pump wear out? What is the mechanism that allows soft biological tissue to outperform every mechanical device humanity has ever built? That question would take another 3 centuries to begin to answer. And the answer, when it came, required tools that Harvey couldn't have imagined: electron microscopes, electrophysiology equipment, biochemical analysis at the molecular level. It required, in other words, a completely different way of looking at the heart. Not at its chambers and valves, not at the blood it moves, but at the cells it is made of. At the machinery running inside each one of those cells, invisible to the naked eye, operating according to principles of physics and chemistry that the ancient world had no framework to even imagine. That is where we are going next. Because once you understand what is happening inside a single cardiac muscle cell, once you see the architecture, the electrical system, the metabolic engine that keeps it running, the mystery doesn't disappear. It deepens into something that begins to look less like a biological accident and more like a solution to an engineering problem that took hundreds of millions of years to solve. Modern science has come a long way since Galen, but the heart, it turns out, has been keeping secrets that even Harvey never suspected. Let's slow down here. Not because what comes next is complicated, but because what comes next is the kind of thing that, once you see it clearly, you cannot unsee. And it deserves the attention that most biology textbooks never give it. The kind of attention that lets you look at a structure and actually understand why it is the way it is. Not just what it looks like, why it looks that way, what problem each feature is solving, what would happen if any single element were even slightly different. Because the heart is not just anatomically interesting, it is anatomically perfect for what it does. And that perfection, once you start tracing it, reveals itself in every dimension. In the gross structure you can hold in your hand, in the geometry of its chambers, in the architecture of its valves, in the arrangement of its muscle fibers, and in the way all of these elements work together to produce a mechanical performance that no human engineer has come close to replicating. Start with size. The adult human heart is approximately the size of a closed fist. You have, right now, a reasonably accurate scale model of your own heart at the end of your arm. Its weight falls between 250 and 350 grams in most healthy adults, roughly equivalent to a large apple or a can of soup with about a third of the liquid poured out. It sits in the mediastinum, the central compartment of the chest cavity, positioned slightly to the left of the body's midline, tilted at an angle so that its apex, its lower pointed tip, aims down and to the left, while its broad upper base connects to the great vessels that carry blood to and from the lungs and body. That positioning is not arbitrary. The heart is suspended in a fibrous sac called the pericardium, which anchors it to the diaphragm below, the sternum in front, and the great vessels above, holding it stable against the mechanical forces generated by its own contractions. Without that anchoring, each heartbeat would send the organ lurching sideways inside the chest. The pericardium solves this problem with a double-walled design, an outer fibrous layer that resists overstretching, and an inner serous layer that produces a thin film of lubricating fluid, reducing friction between the beating heart and the surrounding structures to nearly zero. The engineering solution to the problem of a self-vibrating organ in a confined space is elegant and ancient. It appears in virtually every vertebrate lineage that has a chambered heart. Now look at the chambers. The heart has four: two atria, upper receiving chambers, and two ventricles, lower pumping chambers. The right side of the heart handles pulmonary circulation. It receives oxygen-depleted blood returning from the body through the great veins and pushes it through the pulmonary arteries to the lungs, where it picks up oxygen and releases carbon dioxide. The left side handles systemic circulation. It receives the newly oxygenated blood returning from the lungs and drives it out through the aorta to supply every tissue in the body. These two circuits, pulmonary and systemic, operate simultaneously, in perfect coordination, driven by a single organ. The right ventricle and left ventricle contract at exactly the same moment, every beat, so that the volume of blood entering the pulmonary circuit always equals the volume entering the systemic circuit. If this balance were disrupted even briefly, if the left ventricle pumped significantly more blood than the right, or vice versa, for even a few minutes, fluid would begin to accumulate in either the lungs or the peripheral tissues, with rapidly life-threatening consequences. The fact that this balance is maintained automatically, continuously, without any external regulation, across a lifetime of varying demands, is itself a remarkable engineering achievement. The mechanism that enforces it is called Starling's law, a principle described by the British physiologist Ernest Starling in 1914, which states that the force of cardiac muscle contraction is proportional to the initial length of the muscle fiber. In simpler terms, the more blood that fills a chamber before it contracts, the harder it contracts to expel it. This means that if the right ventricle sends slightly more blood to the lungs, the left atrium fills slightly more, the left ventricle stretches slightly further, and it automatically contracts with proportionally greater force to clear the extra volume. The system is self-balancing at the mechanical level, requiring no hormonal or neural intervention for moment-to-moment equalization. Ernest Starling identified this principle by studying isolated heart muscle preparations in the laboratory. But the principle itself was built into cardiac muscle by evolution hundreds of millions of years before Starling was born. Now look at the walls. The wall thickness of the four chambers varies dramatically, and that variation is one of the most instructive examples of form following function anywhere in human anatomy. The atria have thin walls. Their job is simply to receive blood from the veins and move it a short distance into the ventricles below. They generate relatively low pressures, around 8 to 12 millimeters of mercury during contraction, and their wall thickness reflects this modest demand. You could call them staging areas rather than pumping chambers. Elegant, efficient, not overbuilt for the task they perform. The right ventricle has a moderately thick wall. It needs to generate enough pressure to push blood through the pulmonary circuit, through the lungs and back, but the pulmonary circulation is a low-resistance system. The vessels of the lungs are short, numerous, and relatively compliant. The right ventricle typically generates peak pressures of around 25 to 30 millimeters of mercury. Its wall reflects this, thicker than the atria, but not dramatically so. The left ventricle is in a different category entirely. Its wall, in a healthy adult, is approximately 8 to 12 millimeters thick, roughly 3 times the thickness of the right ventricular wall. Under a cross-section, it appears almost cylindrical, its muscle mass arranged in complex overlapping spirals that allow it to generate peak systolic pressures of 100 to 140 millimeters of mercury with every contraction. This is the pressure that drives blood not just to the fingertips, but to the kidneys, the liver, the intestines, the legs, the brain, every organ and tissue in the systemic circulation against the full resistance of tens of thousands of miles of branching vessels. The left ventricle is the hardest working muscle chamber in the human body, by a significant margin, and here is what makes this particularly interesting from an engineering perspective. The left ventricle does not pump blood like a simple piston, pushing fluid straight out of a cylinder. Its muscle fibers are arranged in a helix. Outer fibers run in one spiral direction, inner fibers run in the opposite direction. When they contract together, the ventricle doesn't just squeeze, it rings. The apex twists slightly counterclockwise, while the base rotates clockwise, producing a motion that has been compared, accurately, to wringing water from a wet cloth. This wringing motion is dramatically more efficient at ejecting fluid than a simple squeeze would be, extracting maximum volume from minimum muscle mass. Cardiac surgeons who observe this twisting motion during open-heart procedures describe it as one of the most remarkable things they have ever seen. Sports medicine researchers have spent decades trying to understand and replicate this biomechanical principle in prosthetic devices. No synthetic material yet produced can match the efficiency of the spiral myocardium. Now let's talk about the valves. The heart has 4 valves, and they are among the most mechanically sophisticated structures in the human body. Their job is straightforward in principle: allow blood to flow in one direction, prevent it from flowing back. But the engineering required to do this reliably, at the required precision, 100,000 times a day, for a human lifetime, is anything but straightforward. The mitral valve, on the left side between the atrium and ventricle, and the tricuspid valve on the right side, are called atrioventricular valves. They consist of thin, flexible leaflets, flaps of tissue attached at their bases to a fibrous ring, and at their free edges to slender tendinous cords called chordae tendineae, which anchor them to small muscular projections on the ventricular wall called papillary muscles. When the ventricle fills with blood, the leaflets hang open passively, allowing flow from atrium to ventricle. When the ventricle contracts, the rising pressure in the ventricle pushes the leaflets upward and closes them. But the chordae tendineae, tightened by the contracting papillary muscles, prevent them from being pushed backward into the atrium. The valve closes with perfect timing, holds against the full ventricular pressure, and opens again as soon as that pressure drops. This mechanism, the coordinated interplay of leaflets, chordae, and papillary muscles, is so mechanically sophisticated that biomedical engineers designing prosthetic valves have struggled for decades to match its performance. The best mechanical heart valves currently available produce subtle but measurable turbulence in blood flow. They require patients to take blood thinners for the rest of their lives to prevent clotting around the valve components. They are remarkable human achievements, and they are still inferior, in multiple measurable ways, to the tissue valve they replaced. The aortic valve, guarding the exit from the left ventricle into the aorta, is architecturally different. 3 crescent-shaped cusps arranged in a ring, like 3 equally sized scoops facing each other, their concave surfaces forming a tripartite pocket that catches blood attempting to flow backward from the aorta into the ventricle and snaps the valve shut with extraordinary speed and precision. The geometry of these 3 cusps is not arbitrary. It is the mathematically optimal arrangement for generating the fastest, most complete closure possible given the pressure dynamics of the aortic root. Fluid mechanics simulations published by researchers at Stanford University in 2017 confirmed that the 3-cusp design produces lower stress concentrations in the valve tissue than either 2-cusp or 4-cusp alternatives, which is why congenital bicuspid aortic valves, present in approximately 1 to 2% of the population, are associated with significantly higher rates of valve deterioration over a lifetime. Evolution, working across hundreds of millions of years, arrived at the 3-cusp design. Stanford's computational models confirmed it was optimal. That convergence is not coincidence. But here is the thing about all of this beautiful architecture: the spiral myocardium, the self-balancing chambers, the mechanically optimal valves. Anatomy is the blueprint. Anatomy tells you what the instrument looks like. It doesn't tell you how the music is made. Because the heart's extraordinary endurance is not primarily a structural achievement. A structure made of biological tissue, no matter how elegantly designed, should still wear out over 3 billion cycles. Steel wears out, titanium wears out, carbon fiber wears out. The reason the heart doesn't wear out is not primarily in its shape, it is in its cells. In the metabolic and electrical machinery operating inside each cardiac muscle cell, machinery so sophisticated, so specifically adapted to continuous operation, that it essentially rewrites the rules by which muscle tissue is supposed to function. The myocardium is not just anatomically different from skeletal muscle, it is fundamentally different at the cellular level, different in its energy systems, different in its electrical properties, different in the way individual cells communicate with each other, different in ways that, once you understand them, make the heart's endurance not just impressive, but almost logically inevitable. This is where the real answer lives. Not in the chambers or the valves or the spiral fibers, though all of those are extraordinary, but in the cardiomyocyte itself. In what happens inside that cell, billions of times a day, that makes everything else possible. That is where we are going next, and I promise you, what happens at the cellular level is stranger, more precise, and more beautiful than anything the anatomy alone prepares you for. Let's go smaller, much smaller. Everything we have looked at so far, the chambers, the valves, the spiral muscle fibers, the pressure differentials, the self-balancing hydraulics of a dual circulation system, all of that is visible, in principle, to the naked eye. A careful anatomist with good lighting and steady hands could have described most of it in the 17th century. Vesalius got close. Harvey understood the mechanics. Even the valve geometry was well characterized by the 18th century. But none of that explains the central mystery. None of that tells us why the heart doesn't wear out. Because the answer to that question does not live at the scale of chambers and valves. It lives at a scale that required the invention of the electron microscope to even begin to see. Inside the individual cardiac muscle cell, in the molecular machinery that keeps it contracting and resting and contracting again 100,000 times a day for a lifetime, without ever crossing the threshold into the kind of fatigue that stops every other muscle in your body. A cardiomyocyte, a cardiac muscle cell, is, by the standards of human cells, large. Roughly 100 micrometers long and 20 to 30 micrometers in diameter. That is still invisible to the naked eye. You could line up 10 of them across the width of a single human hair. But in cellular terms, it is substantial. And what that cell contains in the arrangement and density of its internal structures is unlike anything else in the human body. Start with the mitochondria. You probably remember mitochondria from school, the powerhouse of the cell, the organelle that produces adenosine triphosphate, ATP, the universal energy currency of biological systems. Every cell in your body contains mitochondria. Most cells have hundreds. The number varies with the energy demands of the tissue. Liver cells, which perform enormous amounts of chemical processing, have roughly 1,000 to 2,000 mitochondria per cell. Skeletal muscle cells, which need to generate significant mechanical force, have mitochondria that account for roughly 2 to 8% of the cell's total volume under resting conditions, increasing somewhat with endurance training. In a cardiomyocyte, mitochondria occupy between 30 and 40% of the cell's total volume. 30 to 40%. To put that in perspective, roughly 1/3 of everything inside a cardiac muscle cell is dedicated to energy production. Not to contractile proteins, not to structural scaffolding, not to the cell's nucleus or its protein synthesis machinery. 1/3 of the entire cellular interior is packed, almost crystalline in its density, with mitochondria. Researchers at the Max Planck Institute of Biophysics in Frankfurt published electron microscopy imaging in 2021, showing the three-dimensional architecture of mitochondria in human cardiomyocytes. And the images are genuinely startling. The mitochondria are not scattered randomly through the cell interior, as they tend to be in other cell types. They are arranged in precise columns alongside the contractile units, the sarcomeres, that generate the mechanical force of contraction. Each sarcomere has mitochondria positioned immediately adjacent to it, on both sides, like a power station built directly next to the factory it supplies. The logic of this arrangement is ruthless efficiency. ATP has an extremely short half-life in active muscle tissue. It is consumed within seconds of production. Getting ATP from a mitochondrion to a sarcomere fast enough to sustain continuous contraction requires that the distance between producer and consumer be minimized as much as possible. The cardiomyocyte has solved this problem by essentially eliminating the distance entirely. The power plant is inside the factory wall. But the mitochondrial density alone does not fully explain cardiac endurance. It explains energy supply. It does not explain why the cell itself, the contractile machinery, the membranes, the proteins, does not degrade over 3 billion cycles the way mechanical components degrade over far fewer. For that, we need to look at how the cardiomyocyte handles calcium. Calcium is the trigger of muscle contraction. In every muscle cell, skeletal, smooth, or cardiac, the signal to contract ultimately arrives as a surge of calcium ions flooding into the space around the contractile proteins. Calcium binds to a regulatory protein called troponin, which shifts position and exposes binding sites on the actin filament, allowing myosin heads to attach, pull, and generate force. When calcium is removed, pumped back out of the cytoplasm into storage compartments inside the cell, troponin returns to its blocking position, the myosin heads detach, and the muscle relaxes. This calcium cycle, release, contraction, reuptake, relaxation, is the fundamental mechanism of all muscle function. But the way it operates in cardiac muscle is dramatically different from the way it operates in skeletal muscle. And those differences are central to understanding why the heart can work continuously without fatigue. In skeletal muscle, the signal to contract arrives through a motor nerve, an electrical impulse from the nervous system that you either consciously generate or that your spinal cord generates reflexively. Each nerve impulse triggers a single muscle fiber to contract. Multiple impulses arriving in rapid succession cause the fiber to enter a sustained fused contraction called tetanus, the kind of sustained grip you feel when you hold something tightly for a long time. Tetanus is normal and necessary for skeletal muscle function, but it is also fatiguing. Sustained calcium release without adequate recovery time depletes ATP, accumulates metabolic byproducts, and eventually produces the burning, weakening sensation that tells you a muscle has been pushed to its limit. Cardiac muscle cannot tetanize. This is not an accident or a limitation. It is a precisely engineered feature. And it is the single most important reason the heart can work continuously without fatigue. The mechanism that prevents cardiac tetanus is called the refractory period, and it is built directly into the electrical properties of the cardiomyocyte membrane. Every time a cardiac muscle cell fires, every time it generates the electrical event, called an action potential that triggers calcium release and contraction, the cell membrane enters a state of temporary electrical inexcitability. During this refractory period, which lasts approximately 250 to 300 milliseconds in a human cardiomyocyte at resting heart rate, the cell physically cannot generate another action potential, no matter how strong the incoming signal. The ion channels that carry the electrical current are inactivated, closed in a configuration that requires time to reset before they can open again. 250 to 300 milliseconds is not a long time. It is roughly a quarter of a second, but it is precisely calibrated to match the duration of cardiac muscle contraction, meaning that the refractory period ends at almost exactly the moment the contraction completes and the muscle begins to relax. The cell becomes excitable again just as it finishes its work. Another signal arrives, or the cell's own pacemaker activity generates one, and the cycle repeats. The result is that cardiac muscle can never sustain a contraction longer than a single beat. It contracts, it relaxes, it recovers, it contracts again. The recovery is not optional. It is not something the cell chooses to do when it has time. It is mandatory, enforced by the physics of ion channel kinetics, built into the electrical architecture of the membrane at a level that no external signal, no matter how powerful, no matter how insistent, can override. Your heart rests between every single beat, 100,000 times a day, not because it is tired, because its architecture demands it, because the recovery is baked into the mechanism at the most fundamental level. Don't scroll past this. Let it settle for a moment. This is the cellular answer to the engineering mystery. Not that the heart never rests, but that it rests constantly, automatically, in intervals so brief that they are invisible to conscious experience, but so precisely timed that they allow the contractile machinery to reset completely before the next demand arrives. But there is another layer to this story. Because the refractory period prevents fatigue at the level of the individual cell, it does not, by itself, explain how billions of individual cells coordinate to produce a single unified contraction of the entire heart muscle simultaneously, which is what is required for effective pumping. A heart in which different regions contracted at different times, each following its own electrical schedule, would not pump blood. It would quiver uselessly, which is in fact exactly what happens during ventricular fibrillation, and why ventricular fibrillation is rapidly fatal without intervention. The coordination mechanism is the intercalated disc. Cardiomyocytes are not independent units connected by nerve fibers, the way skeletal muscle fibers receive individual commands from motor neurons. They are physically coupled to each other through specialized junctions called intercalated discs, dense interlocking structures at the ends of each cell that contain, among other components, structures called gap junctions. Gap junctions are protein channels that create direct cytoplasmic connections between adjacent cells, literal openings in the cell membranes that allow ions, small molecules, and critically electrical current to pass freely from one cell to the next. The functional consequence of this architecture is profound. When one cardiomyocyte fires an action potential, the electrical signal does not stop at the cell boundary and wait to be transmitted to the next cell through a synapse, the way signals travel between nerve cells or between nerves and skeletal muscle fibers. It passes directly through the gap junctions into the adjacent cell, which fires immediately, passing the signal to its neighbors, which fire immediately, propagating the electrical wave across the entire myocardium in a fraction of a second. The conduction velocity through gap junctions in cardiac muscle is not as fast as a myelinated nerve fiber, but it is fast enough. The electrical wave that triggers a heartbeat travels from its origin point in the sinoatrial node, in the upper right atrium, across both atria in approximately 80 milliseconds, pauses briefly at the atrioventricular node to allow the atria to finish contracting and the ventricles to fill, and then propagates through a specialized fast conduction system, the bundle of His and the Purkinje fibers, to activate both ventricles almost simultaneously within another 40 to 80 milliseconds. The entire electrical event, from initiation to complete ventricular activation, takes less than 200 milliseconds, 1/5 of a second. This architecture, gap junction coupling, combined with specialized fast conduction pathways, transforms billions of individual cells into a single functional unit. Cardiomyocytes behave, electrically and mechanically, as a syncytium, a coordinated mass that acts as one. When the signal arrives, they all fire together. When the refractory period begins, they all rest together. When the next signal arrives, they all fire together again. This is why the heart pumps effectively, and this is also why certain cardiac arrhythmias, conditions in which this orderly, coordinated electrical sequence breaks down, are so immediately dangerous. The mechanical performance of the heart depends entirely on the precision of its electrical choreography. Disrupt the choreography, and the pump fails instantly, regardless of how healthy the individual muscle cells are. There is one more cellular feature worth understanding before we zoom back out to the level of the whole organ, and it is perhaps the most quietly remarkable fact about cardiac muscle cells that most people never learn. Cardiomyocytes in adult humans essentially do not divide. Almost every other cell type in the human body maintains some capacity for renewal. Skin cells turn over completely every 2 to 4 weeks. The lining of the intestine replaces itself every 3 to 5 days. Liver cells can regenerate dramatically after injury. A liver reduced to 30% of its original mass can regrow to near normal size within months. Even neurons, long believed to be entirely non-renewable, have been shown to undergo limited neurogenesis in specific brain regions throughout life. Cardiomyocytes renew at a rate of less than 1% per year in young adults, declining to near zero in older age. Research published in the journal Science in 2009 by Jonas Friesen and colleagues at the Karolinska Institute in Stockholm using radiocarbon dating of cardiac DNA, a technique that exploited the elevated atmospheric carbon-14 levels produced by nuclear weapons testing in the 1950s and 1960s as a biological timestamp, established that the majority of cardiomyocytes in an adult human heart were formed before birth or in early childhood and remain in the body for the person's entire lifetime. The cells beating in your heart right now are, most of them, as old as you are. They have been contracting since before you drew your first breath. They will contract until the moment you draw your last. They do not wear out. They do not divide and replace themselves. They simply keep working, maintained, repaired at the molecular level through continuous protein turnover and quality control mechanisms that replace damaged components without ever stopping the machine. For a human lifetime, no engineer has built anything that operates on this principle and achieves this durability. No material science has produced a component that self-repairs at the molecular level while continuing to function at full capacity. No maintenance protocol has achieved what the cardiomyocyte achieves simply by existing. But the cell does not work alone. The cardiomyocyte is extraordinary, and it is embedded in a system of systems, connected to the nervous system, the endocrine system, the vascular system, the kidneys, the brain, in ways that make the whole profoundly more complex and profoundly more fragile than any of the individual parts suggest. That is what we need to look at next. Because the heart's endurance is real, but its vulnerability is also real. And understanding one without the other gives you only half the picture. The other half, the half that explains why heart disease is the leading cause of death in every developed nation on Earth, is waiting in the next part of this story. Picture a man named Robert. He is 63 years old. He lives in a mid-sized city in the American Midwest, Columbus, Ohio, or Kansas City, or Indianapolis, somewhere with cold winters and a culture of long workdays and meals eaten quickly. He spent 30 years managing logistics for a regional trucking company. He is not dramatically unhealthy. He doesn't smoke. He drinks moderately. He walks the dog most evenings, maybe a mile, maybe a mile and a half. His doctor has told him his blood pressure is a little high, 140/90, consistently for the past several years, and that he should probably lose 15 pounds and watch his sodium intake. Robert has been meaning to get around to both of those things. One Tuesday morning in February, Robert is sitting at the kitchen table, drinking his second cup of coffee and reading something on his phone when he feels a strange sensation in the center of his chest. Not pain exactly. Pressure. A heaviness, like someone has placed a hand flat against his sternum and is pushing, gently but insistently, from the outside in. The feeling lasts about 2 minutes and then fades. Robert notices it, frowns, finishes his coffee, and drives to work. That evening, the pressure comes back. This time it radiates into his left shoulder. It lasts 4 minutes. His wife notices that he has gone pale and asks if he is all right. Robert says he is fine. He takes 2 antacid tablets and goes to bed. At 2:17 in the morning, Robert wakes up with the worst pain he has ever felt in his life. What Robert is experiencing, what is happening inside his chest at 2:17 in the morning while his wife calls emergency services and Robert sits on the edge of the bed trying to breathe, is not the heart suddenly stopping. It is something more specific and in some ways more insidious. A plaque of cholesterol and inflammatory tissue that has been silently accumulating inside a branch of his left coronary artery for perhaps 15 years has ruptured. The rupture has triggered a blood clot to form at the rupture site, rapidly blocking the artery, and the region of cardiac muscle downstream from that blockage, a wedge of myocardium that has been receiving oxygen through that artery every second of every day for 63 years, has just been cut off. Not weakened, not reduced, cut off, completely. Cardiac muscle can survive without oxygen for approximately 20 minutes before cell death begins. After 40 minutes of complete ischemia, the damage becomes substantial and largely irreversible. After 90 minutes, a significant portion of the affected territory is gone, not temporarily injured, not weakened, but dead. Replaced over the following weeks by scar tissue that cannot contract, cannot conduct electrical signals, and cannot contribute to the heart's pumping function in any meaningful way. Robert reaches the hospital 38 minutes after his wife's call. The interventional cardiology team opens the blocked artery with a balloon catheter and places a stent within another 45 minutes of his arrival. His door-to-balloon time, the interval between entering the emergency department and restoration of coronary blood flow, a metric that every cardiology department in the world tracks obsessively because every additional minute correlates with measurable additional muscle loss, is 43 minutes. This is good. This is well within the 90-minute target that the American Heart Association considers the threshold for acceptable outcomes. Robert survives. He goes home after 5 days. He takes 5 medications. He comes back for cardiac rehabilitation. His ejection fraction, the percentage of blood the left ventricle expels with each beat, which in healthy adults runs between 55 and 70%, has dropped to 41%. It will recover partially over the following months. It will probably never fully return to normal. The scar in Robert's myocardium is permanent. I am telling you Robert's story not to frighten you, though if it prompts you to make a phone call to a doctor you have been putting off, that is not the worst outcome. I am telling you his story because it is the most instructive lens through which to understand the fifth and most complex aspect of the heart's biology. How deeply, how completely, how inescapably the heart is woven into every other system in the body. And what happens to all of those systems when the heart begins to fail? Because a heart attack is not just a heart event, it is a whole body event, and the cascade of responses it triggers reveals, more clearly than anything else, the true nature of the heart's role in human physiology. Begin with the kidneys. The kidneys receive approximately 20% of cardiac output at rest, roughly 1 liter of blood per minute flowing through 2 organs that together weigh less than 300 grams. They use this blood flow not just to filter waste products, but to monitor circulatory pressure and volume continuously. Specialized cells in the kidney called juxtaglomerular cells are exquisitely sensitive to changes in arterial pressure. When pressure drops, as it does when cardiac output falls after a heart attack, these cells interpret the drop as a signal that blood volume is too low, and they respond by releasing an enzyme called renin into the bloodstream. Renin initiates a cascade. It cleaves a circulating protein called angiotensinogen into angiotensin 1, which is then converted by angiotensin-converting enzyme in the lungs into angiotensin 2, one of the most potent vasoconstrictors in the human body. Angiotensin 2 simultaneously narrows blood vessels throughout the body, raising resistance and therefore pressure, and stimulates the adrenal glands to release aldosterone, a hormone that causes the kidneys to retain sodium and water, expanding blood volume. The intent of this cascade, evolutionarily speaking, is to compensate for blood loss. If a prehistoric human was hemorrhaging, this response would raise blood pressure, preserve circulating volume, and buy time for survival. It is an elegant emergency response to acute volume depletion. But in heart failure, it is catastrophic. The heart isn't losing blood. It is failing to pump the blood it has. The kidneys cannot distinguish between these two situations, both present as reduced arterial pressure, so they activate the same compensatory cascade. The blood vessels constrict, increasing the resistance that the already weakened heart must pump against. The kidneys retain fluid, increasing the volume of blood the heart must move. Both responses make the heart's job harder at precisely the moment when the heart is least capable of doing it. The very systems designed to protect the organism are accelerating its decline. This vicious cycle, reduced cardiac output, triggering neurohormonal responses that further burden the failing heart, is the central mechanism of progressive heart failure. It explains why heart failure is not a static condition, but a progressive one. Why patients who survive a heart attack and appear stable can deteriorate months or years later as the compensatory mechanisms that initially helped them begin to cause cumulative damage. Why the medications that have most dramatically improved survival in heart failure, ACE inhibitors, beta blockers, aldosterone antagonists, work not by strengthening the heart directly, but by interrupting these compensatory cascades before they cause irreversible harm. Now consider the nervous system. The heart is under constant dual regulation from the autonomic nervous system, the branch of the nervous system that operates below conscious awareness, controlling heart rate, blood pressure, digestion, breathing rate, and dozens of other vital functions without any deliberate input from you. The sympathetic division of the autonomic nervous system accelerates the heart, increases the force of contraction, and prepares the body for physical or psychological demands. The parasympathetic division, mediated primarily through the vagus nerve, slows the heart and promotes recovery and rest. In a healthy person, these two systems are constantly balanced against each other, producing moment-to-moment variations in heart rate that reflect the body's changing demands. This variability, the subtle acceleration as you inhale and deceleration as you exhale, the slight quickening when you stand up, and the return to baseline when you sit down, is called heart rate variability, and it is one of the most sensitive markers of overall cardiovascular health available without invasive testing. Research published in The Lancet in 1997 and subsequently confirmed in numerous large cohort studies has established that reduced heart rate variability is an independent predictor of mortality after heart attack, more predictive in some analyses than ejection fraction or the extent of coronary artery disease. What reduced heart rate variability reflects is a shift in autonomic balance, specifically a relative withdrawal of parasympathetic influence and a dominance of sympathetic activity. In the context of heart failure, this shift is driven by the same neurohormonal activation that affects the kidneys. Chronically elevated sympathetic tone causes a persistent elevation of heart rate, increases myocardial oxygen demand, and over time desensitizes the heart muscle to the catecholamines, adrenaline and noradrenaline, that the sympathetic system uses as its chemical messengers, leading to progressive deterioration of cardiac function. The brain, meanwhile, is responding to cardiac signals in ways we are only beginning to understand. The heart contains an extensive network of sensory neurons, sometimes called the intrinsic cardiac nervous system, or more colloquially, the heart's own nervous system, that monitors mechanical stretch, chemical environment, and electrical activity within the cardiac chambers and transmits this information to the brain via afferent nerve fibers. Researchers at the HeartMath Institute in California and at several major academic medical centers have published evidence over the past 2 decades suggesting that the information flowing from the heart to the brain is not merely monitoring data, but actually influences emotional processing, cognitive function, and stress reactivity in ways that remain incompletely characterized. The heart sends more neural signals to the brain than the brain sends to the heart. This fact, documented in standard neuroanatomy but rarely discussed outside specialist literature, suggests a model of cardiac-cerebral interaction considerably more bidirectional and complex than the simple command and control framework that most people assume. Now consider also what happens to the lungs when the heart fails. The left ventricle, weakened by a heart attack or by years of uncontrolled hypertension or by any of dozens of other causes, begins to fall behind its workload. Blood returning from the lungs through the pulmonary veins backs up because the left side of the heart cannot clear it fast enough. The pressure in the pulmonary veins rises when pulmonary venous pressure exceeds a critical threshold, approximately 25 to 30 millimeters of mercury. Fluid begins to leak from the pulmonary capillaries into the air spaces of the lung. This is pulmonary edema. The lungs fill with fluid. Gas exchange becomes increasingly impaired. The patient feels as though they are drowning, because in a clinical sense, they are. This is the constellation of symptoms that brings patients to emergency departments in the middle of the night with oxygen saturations of 80% and respiratory rates of 35 breaths per minute, unable to lie flat because lying flat allows the fluid to distribute more evenly across the lung bases and worsens the sensation of suffocation. They sit upright in bed, leaning forward, using every accessory muscle in the neck and chest to breathe. Their skin mottled and pale, their hearts racing at 130 beats per minute in a desperate attempt to compensate for the reduced output of each individual beat. These are the downstream consequences of a muscle the size of your fist, weighing less than 350 grams, beginning to fail. And what is remarkable, and what is worth sitting with for a moment before we move to the final part of this story, is not that the system eventually fails. Everything fails eventually. What is remarkable is how long, and how stubbornly, and with what extraordinary resourcefulness the human body fights to prevent it. Starling's law kicks in, stretching the remaining healthy muscle to contract more forcefully. The neurohormonal system activates to preserve pressure. The surviving cardiomyocytes hypertrophy. They grow larger and stronger to compensate for the ones that have been lost. The electrical conduction system rewires slowly and imperfectly around the damaged territory. New blood vessels sprout at the margins of the infarct zone in a process called angiogenesis, attempting to restore perfusion to the border regions. None of these compensations are sufficient to fully replace what has been lost, but they are remarkable. They are the body's full effort, mobilized without deliberate intention, executing a recovery program of extraordinary complexity in response to an injury that for most of human evolutionary history would have been rapidly fatal. Robert goes home from the hospital. He takes his medications. He walks every day. His heart, damaged, scarred, permanently changed, keeps beating. It has adapted to its new reality. It is not the heart it was, but it is still, improbably, magnificently doing its job. That is what systems do when they are designed, or evolved, with enough redundancy, enough flexibility, enough capacity for self-reorganization that even significant damage cannot fully stop them. But there are limits, and science still does not fully understand where those limits are, or why some people reach them quickly, while others never seem to reach them at all. That mystery, and what it means for how we understand the heart, the body, and life itself, is what the final part of this story is about. There is a photograph taken in 1929 that very few people have seen. It was taken in a laboratory at the Rockefeller Institute in New York City, and it shows a small glass flask sitting on a laboratory bench, connected by rubber tubing to a simple pump and a reservoir of nutrient solution. Inside the flask, barely visible, is a piece of tissue approximately the size of a thumbnail. The tissue is pink, and it is moving. It is a fragment of embryonic chicken heart, and it has been beating continuously, outside of any living body, for 17 years. The experiment was the work of Alexis Carrel, a French surgeon who had won the Nobel Prize in Physiology or Medicine in 1912 for his work on vascular suturing, the techniques that made organ transplantation theoretically possible decades before it became practically achievable. Carrel was obsessed with the question of cellular immortality. He believed, and spent decades attempting to prove, that cells removed from a living organism and maintained in the correct nutrient environment could survive and function indefinitely. That death was not a cellular inevitability, but an environmental one, imposed on cells by the deteriorating internal environment of the aging body, rather than built into the cells themselves. His chicken heart culture ran from January 17, 1912 until 1946, 34 years of continuous beating, outliving Carrel himself, who died in 1944. It became one of the most famous scientific demonstrations of the 20th century, cited in newspapers and popular magazines as proof that life, at its cellular core, might be potentially immortal. There was one problem. The experiment almost certainly could not have produced the results Carrel claimed. Subsequent attempts to replicate it, using the careful aseptic techniques that became standard in cell culture after World War II, consistently failed. The most likely explanation, accepted by most historians of science today, is that the nutrient solution Carrel's team used to feed the culture, prepared from embryonic chicken tissue extract, inadvertently introduced fresh living cells with each feeding, and that what appeared to be a continuous 34-year culture was actually a continuously refreshed population of new cells. The heart fragment was not immortal. It was being quietly, invisibly replenished. I am not telling you this story to debunk Carrel or to make a point about scientific fraud. There is genuine debate about whether the error was deliberate or inadvertent. I am telling you this story because of what it reveals about the nature of the question Carrel was asking, and because the real answer to that question, the actual mechanism by which cardiac cells maintain their function across a human lifetime, turns out to be something far stranger, and in some ways far more interesting than immortality. Carrel was asking the wrong question. The heart is not immortal. Its cells do not live forever. What they do is something more subtle, and I would argue, more profound. They maintain themselves, continuously, dynamically, at the molecular level, while never stopping the work they were designed to do. Every protein in a cardiomyocyte is eventually degraded and replaced. The contractile proteins, actin and myosin, the molecular motors that generate the force of each heartbeat, turn over with half-lives measured in days to weeks. The mitochondrial proteins that drive energy production are replaced on timescales of days. The ion channel proteins that govern the electrical properties of the cell membrane are continuously synthesized, inserted, and degraded. The entire molecular machinery of the cardiac muscle cell is in a constant state of renewal, with damaged or worn components identified, tagged for destruction, dismantled, and replaced without ever interrupting the cell's continuous function. This process, called protein quality control or proteostasis, is not unique to cardiomyocytes. Every cell in the body does it. But in most cell types, there is a backup option available when the burden of molecular damage becomes too great. The cell divides. It produces two daughter cells, each inheriting a share of the original cell's components, plus freshly synthesized replacements, and the accumulated damage is effectively diluted away. Cell division is the cellular equivalent of a factory shutdown and retooling, a pause that allows comprehensive repair. Cardiomyocytes cannot do this, or rather, they essentially cannot do this. The rate of cardiomyocyte division in adult human hearts is so low, less than 0.5% per year, that it is functionally negligible for repair purposes. The cells that beat in your heart today are, overwhelmingly, cells that have been beating since before you could walk. They cannot divide their way out of accumulated damage, so they have developed, across hundreds of millions of years of vertebrate evolution, the most sophisticated molecular maintenance system in the human body. Autophagy, the cellular self-digestion process by which damaged organelles and protein aggregates are sequestered, broken down, and recycled, operates at higher basal rates in cardiomyocytes than in almost any other cell type. The ubiquitin proteasome system, which tags and destroys misfolded or damaged proteins before they can accumulate and disrupt cellular function, is under extraordinary selective pressure in cardiac tissue. Mutations that impair this system in cardiomyocytes produce severe cardiomyopathies, even in young individuals. Heat shock proteins, molecular chaperones that stabilize proteins under stress and refold those that have been damaged, are constitutively expressed at high levels in cardiac muscle, providing continuous protection against the mechanical and thermal stresses of contraction. The cardiomyocyte does not rest in order to repair. It repairs while working, continuously, in real time, molecule by molecule, organelle by organelle, maintaining function while simultaneously renewing the machinery that produces it. There is no human technology that operates on this principle. We do not have factories that retool their own machinery while running at full production. We do not have engines that replace their own components while driving. The closest analogies, self-healing materials, autonomous maintenance systems in spacecraft, adaptive manufacturing robots, are crude approximations of a process that biological evolution refined over 600 million years of continuous iteration. And yet here it is, in your chest. Right now, step back from the cellular level, step back from the chambers and the valves and the electrical system and the neurohormonal cascades and the systemic connections. Step all the way back to the largest possible view. What is the heart? It is a pump, yes. The most durable, most adaptable, most self-maintaining pump ever produced by any process, biological or technological, in the known history of the Earth. That is a factual statement, not a poetic one. By the metrics of operational lifespan, power-to-weight ratio, dynamic range of output, and capacity for self-repair under continuous operation, no human-engineered device comes close to the performance of a human heart across a full human lifetime. But it is also something else, something that becomes visible only when you have traced the whole picture, when you have followed the electrical signal from its origin in the sinoatrial node, through the gap junctions, down the conduction system, into the spiral myocardium, through the calcium cycle and the refractory period and the mitochondrial matrix, and then back out to the kidneys and the brain and the lungs and every system that listens to the heart and responds to what it says. The heart is not an organ that is connected to other systems. It is the system around which other systems are organized. Remove it, and nothing else can function. Weaken it, and everything else must compensate. Restore it, and the whole organism reconfigures itself around the recovered signal. In this sense, not metaphorically but physiologically, the heart is the center of the body, not the brain, not the gut, the heart. The brain can survive minutes without oxygen only because the heart has been delivering it continuously for every second of the person's life. The gut can process nutrients only because the heart drives the blood flow that carries those nutrients to every cell. The kidneys can filter waste only because the heart maintains the arterial pressure that drives filtration. Everything is downstream of the heart. Everything depends on it. Everything listens to it. This is why, across virtually every human culture in history, the heart has been understood as something more than a mechanical organ. The ancient Egyptians placed the heart on a scale against a feather to judge the worth of a soul. The Aztecs offered hearts to the sun to keep it moving across the sky. Medieval European physicians located the seat of the soul in the heart. Chinese medicine understood the heart as the emperor of the organ system, the sovereign whose health determined the health of the entire realm. We now know that the ancient Egyptians were wrong about the afterlife measurement, that the Aztec cosmology was not literally true, that the soul does not reside in the cardiac muscle. We have electron microscopes and electrophysiology equipment and molecular biology and a century of cardiology that has given us precise, mechanistic accounts of what the heart actually does and how it actually does it. And yet, this is the thing I want you to sit with as this video ends. None of that knowledge diminishes the strangeness of what the heart is. If anything, it deepens it.
There's the
The more
blockage right at
precisely
the
we
bifurcation.
understand the mechanism, the more remarkable
Confirming
the
90%
mechanism becomes.
stenosis, doctor.
The refractory period that prevents fatigue. The gap junctions that create unity from billions of individual cells. The mitochondrial density that provides inexhaustible energy. The proteostasis system that repairs while running. The Starling mechanism that self-balances output between two circuits simultaneously. The neurohormonal sensitivity that adjusts cardiac output to the body's needs in real time, faster than conscious thought. Every one of these features is, individually, an extraordinary engineering solution to a specific problem. Together, they constitute something that exceeds the sum of its parts, a system of such integrated complexity, such mutual interdependence, such elegant self-regulation, that describing it purely in mechanical terms feels, even to many of the scientists who study it most closely, somehow insufficient. The cardiologist Paul Zoll, who developed the cardiac pacemaker in the 1950s, one of the most important medical innovations of the 20th century, said late in his career that the more he understood about the electrical system of the heart, the more convinced he became that he was looking at something that would not have been designed differently, even with unlimited engineering resources and unlimited time. Not because it was perfect, it fails, it has failure modes, it is vulnerable in ways that kill millions of people every year. But because its design philosophy, self-regulation, self-repair, continuous adaptation, hierarchical redundancy, represented an approach to engineering problems that human technology was only beginning, in the latter half of the 20th century, to even conceptualize. He was not making a theological argument, he was making an engineering observation. And it is worth taking seriously, regardless of your metaphysical commitments. Here is what I know for certain. The heart beating in your chest right now has been beating since approximately 3 weeks after conception. Before you had eyes, before you had fingers, before any structure recognizable as a brain had formed. It has beaten through every moment of your life, every fear, every joy, every ordinary Tuesday, every extraordinary crisis. It has beaten through your sleep, and through your panic, and through your grief, and through your laughter. It has beaten approximately 35 million times this year. It will, if you are fortunate, beat 35 million more times next year, and the year after that, and for decades beyond. It has never asked for your attention. It has never demanded acknowledgement. It has simply done its work, contracting and relaxing, cycling calcium and ATP, maintaining its electrical choreography, listening to every system in your body and responding, adjusting, compensating, enduring. There is a 72-year-old woman in Osaka, Japan, whose heart has beaten approximately 2.6 billion times. There is a newborn in a hospital in Lagos, Nigeria, whose heart has beaten perhaps 50 million times since birth, each one a rehearsal for the billions that will follow. There is a man sitting in a waiting room in Toronto right now, about to receive news about his cardiac imaging. His hands folded in his lap, his heart beating at 92 beats per minute because he is frightened. And even his fear, even the adrenaline of this anxious moment, is information that his heart is reading and responding to in real time, automatically, without any instruction from him. We are all, every one of us, being kept alive by the same mechanism, the same refractory period, the same gap junctions, the same mitochondrial density, the same molecular maintenance running silently beneath every moment of conscious experience. That is not a small thing to carry. And knowing it, really knowing it, not as a biology class fact, but as a felt reality, changes something. Not dramatically, not in a way that is easy to articulate, but in the way that real knowledge always changes things. It makes the ordinary strange. It makes the routine miraculous. It makes the silence, when you press your hand to your chest in a quiet room, feel like something worth paying attention to. The heart is not simple. It never was. You were just too close to it to see. Write a number from 1 to 6 in the comments below. That number corresponds to the part of this video that hit you hardest. 1. The opening. The realization that your heart has already beaten over 100,000 times today. 2. The history. Galen's 1,500 years of confident error and Harvey being called insane for being right. 3. The architecture. The spiral myocardium, the self-balancing chambers, the three-cusp valve that Stanford's fluid mechanics confirmed was mathematically optimal. 4. The cell. The refractory period. The gap junctions. The 35% mitochondrial volume. The fact that your cardiomyocytes are as old as you are. 5. The failure. Robert's story. The kidneys misreading the signal. The body fighting against itself in heart failure. The 43 minutes that made the difference. 6. This. The ending. The 2.6 billion beats in Osaka. The newborn in Lagos. The man in the waiting room. Write your number. And if you want, write one sentence about why. And now, one specific ask. Think of someone in your life who has been told they have high blood pressure, or an irregular heartbeat, or that their cholesterol numbers are concerning, and who has been meaning to follow up with a doctor but has been putting it off. Not because they don't care, because the human mind is very good at deferring the things that frighten it. Send them this video, not with a message that says you should watch this. Just send it. Let the heart speak for itself. One share. One person. It costs you 30 seconds. What it might cost them to keep waiting is something none of us can calculate in advance. That's all. Take care of the thing that has been taking care of you.